is Orithro Bonik from IIT Jaipur, and he will be talking about hardness of multiple choice problems.
Thank you, Palash. So I'm going to talk about something that is somehow different than what the previous speakers have talked. It's came from a geometric background, but I hope that it will influence you as well. Okay. So first, let me start by giving an example of a multiple choice problem. Suppose in a multiple choice problem, in this multiple choice problem, you are given a set of color classes. A color class you can think of as a bag, and each bag contains exactly 2 points. For example, here in this figure, there are exactly 6 bags which I have defined by different colors. For example, this is the bag for C4, and here another C4 is a bag of red. So there are 6 bags. It's a set of points or pair of points on a line. Given this set of pair of points, my objective is to choose exactly 1 point from each pair, and we call such a choice a rainbow. For example, in the first choice, we have chosen C1, this C3, then this C4, then this C5, and then this C7. So this is a rainbow. There are 2 rainbows I have shown in this figure. And for example, this is not a rainbow. Why this is not a rainbow? Because it has not covered the color C3, and it has it has selected 2 points from C4. So there are 2 violations here. One, it has not selected any point from one color class, and from one color class it has chosen 2 points. Okay. Now let me define what is a max gap problem is. For any rainbow that is a choice, exactly 1 from each color class, I define the max gap to be the distance, maximum distance between any 2 consecutive chosen points. For example, if these are my set of chosen points, then probably the max gap is between these 2 points. It's the distance between any 2 consecutive points, and it's the maximum such distance. Okay. And in the rainbow minimax gap decision problem, we are asking that whether there exists a rainbow or a choice of points so that the maximum gap between 2 consecutive points are at most d. Does the definition of this problem is clear to you? That what we are trying to find? It's a very simple problem. We are given a pair of points. We want to choose 1 from each pair so that the maximum gap between any 2 consecutive points is minimized. Okay. So this problem was first introduced in TCS paper, and we got that problem from there. But in the paper, the authors have given a 2 approximation algorithm for this problem, but kept the question of whether this problem is NP hard or not open. And starting from that point, you have to find many other such points. For example, here is another point. Again, you are given a set of pair of points and a set of intervals. Now the question is whether there exists a rainbow which pierces all intervals. What do I mean by pierces? A point pierces an interval if the point is present within the interval. For example, here this C1 or say C4 pierces this interval and this interval. Now we are looking for whether there exists a rainbow which pierces all the set of given intervals or not. Similarly, we can define rainbow covering, that instead of given a point, here is the next step towards more generalization. Pair of points, we have pair of intervals. Now can you choose from each pair of interval exactly 1 so that it is covered a given set of points. So this all problems the same thing. So from this you can understand you can define this kind of problem in any setting, even not necessarily geometry. It can be any set and it contains a set of bags, and you have to choose one point from each bag to satisfy certain optimality criteria. Okay. So to show that these problems are NP-hard, I will talk about one satisfiability problem that we call a linear SAT, or in short LSAT. And let me first define what is a LSAT instances. It's of course, it's a SAT. And I hope that everyone, I'm not going into details as what a SAT is. So it's a SAT formula. With the SAT formula, you're given an ordering of the variables or literals. We are given an ordering of the literals on a line. And not only that, you can consider any clause as an interval on that line. That is, consider this clause Z1, Z2, Z3. There has to be 3 consecutive literals Z1, Z2, Z3 such that we can draw this clause as a interval. Is it clear to you what I mean by clause as an interval? Okay. Not only that, there is another condition of a LSAT problem, that each clause can overlap with at most one more clause. What do we mean by overlap? That they can share a literal with one more clause. And it can only share a literal with a clause consecutive to it. We can have a natural ordering of the clauses. For example, C3 here can share a literal with C2 or maybe C4, but not both. They are not allowed to share both of its names. And C6 is not allowed to share any literal with C4. Mind it that I'm talking about literals, not variables. Okay. Now, why this LSAT is important? First of all, it will help us prove that our rainbow problems are hard. But moreover, think of a SAT formula where the clauses are disjoint. That is, no two clauses share the same literal. Then, can we say something about the satisfiability formula? Satisfiable, it is not satisfiable. Only at time you can decide satisfiable or not. It's NP-hard. Okay. So you create, given such a disjoint SAT formula, you create such a bipartite graph. So in one side of this bipartite graph, there are variables, and in the other side there are clauses. Now, if a variable appears in a clause, I put an edge. So there are exactly 2 edges going out of a variable. That it, because the clauses are disjoint, once it is appearing in one SAT, one clause as a negation, and one clause as the variable. Now you can think about it for 5-6 minutes, and you will get that this formula is satisfiable if and only if in this graph you have a matching of size of equals to number of clauses. This is exactly you are trying to find a matching in this graph. Okay. So the point I want to make here is that when the clauses are disjoint, it's polynomial type formula. When the clauses have exactly one intersection with one literal and with exactly one other clause, then this problem becomes NP-hard. So it's the LSAT problem we think is kind of lies very close to the boundary. That's why we think that this LSAT formula is important. we'll show this reduction from general SAT formula, 3 SAT formula. And so suppose we have a CNF formula, and we are assuming that in this CNF formula each variable is each literal is appearing twice, but with the more general reduction, like it, you can extend this reduction to show that even the literals are appearing 3 times, 4 times, 5 times, same reduction will work. But the simplicity of the argument will assume that each literal is appearing at most twice in the same form. Now, what is our aim? From this SAT, we are trying to create an LSAT formula so that if this is satisfiable, the LSAT formula will be satisfiable. If this is not, then LSAT will be not satisfiable. How to create LSAT formula from here? You can see that there will be a lot of, if you take a general SAT, there will be a lot of intersections. Only way that we could think of to deal with that, to create another new set of variables which exactly will mimic the actions of the variables. For example, here for each xi, we are trying to create a set of variables which will exactly mimic the operation of x. That is, when xi is 1, they will be like 1, when it's 0, they will be like 0, something like that. Okay. So, in order to do that, we are creating this following gadget. It's nothing but a set of clauses that for each variable xi, we are creating these 4 clauses. And we are representing pictorially here. So why these clauses? And what we are doing with that? So you can see that these clauses follows the formula of LSAT because they are interacting with only 1, unless we use these literals once again. That we will not use. So here we are using yi. In next we are going to use yi bar. And we are going to do that. We will replace each appearance of xi as a positive form by y bar, and each appearances of negative appearance of xi by zi bar. Okay. So, for example, we will change the given formula by this. Now you can see that there is no overlap between any 2 clauses because we are using completely different literals for each SAT. Now I have to prove that and show that f is satisfiable, only fl is satisfiable. Now suppose the SAT formula is satisfied. Okay? Now what do we do? If xi is assigned, what does it mean by the SAT formula is satisfiable? We have assignment to the variables. In that assignment, if xi is assigned false, here also we assign xi to be false. Now if xi is false, in order to satisfy this clause, we will make y1 as 1 and y2 as 1. Similarly, if xi is 0, we can create similar assignments. Okay. Now, the claim is, if this is satisfiable, then so as f is satisfiable, then fl is satisfiable. Now observe that if xi is assigned 0, now suppose xi is assigned 0, then yij in our assignment, yij bar is assigned 0 and zij bar is assigned 1. You can come back here, you can see this. When xi is assigned 0, yij bar is 0 and yij bar, zij bar is 1. That means they are exactly mimicking the appearances of xi and xi. Yij bar is mimicking xi and yz bar is mimicking xi bar. Okay. Now hence if f is satisfiable, so as f. In the reverse direction, suppose there exists an assignment to the variable so that this fl is satisfiable, then our claim is by that same assignment f is also satisfiable. Now suppose there exists one clause in f that is not satisfiable, then suppose the clause is x2 or x3 bar or x4 bar. Now you know that FL is satisfiable, hence we have satisfied this clause. That means at least one of them has to be 1. Now if F22 bar is 1, hence F22 is, Y22 bar is 1, that means Y22 is 0. Now if Y22 is 0, to satisfy this clause, Xi has to be 1. Similarly, suppose Z33 bar is 1, that means Z3 is 0, then to satisfy this clause, Xi bar has to be 1. Hence, it's not possible that this is satisfiable, but this is not satisfiable. Okay. So hence, we have showed that LSAT is polynomial type solvable. Okay. Now, we go back to our minimax gap problem. So, we will have to show that this problem is hard by showing a reduction from LSAT. So, how to do that? So, our aim is to start with the LSAT formula, and we will prove that. Look at any LSAT formula. There are disjoint set of clauses. Disjoint set of clauses means the clauses that mutually intersects and the clauses that do not intersect. We are calling them the clauses bank, and we will claim that we can create an instance of max gap so that each clause bank is of distance g if and only if they are satisfied. And then etc. So to that, to reduce the interaction between the clause gap, so we use a small trick here that we place certain variables at the end at distance d plus 1 d plus epsilon. What does it mean? That as they are at distance d plus epsilon, to satisfy this, you need to choose the variables x1, q1, q3 and others. So q is chosen. So each clause back is now independent. Now the question is how to choose a clause back, or how to choose the distances between a clause back. So suppose this is one kind of clause back where these two clauses intersect. Now we want to find out what can be the distance between the points so that it is satisfiable if and only if the distance is at most. Okay. So we choose this set of distances. Now you can see, I am not going to the details of the proof, you can see that the one way to satisfy these two clauses to make x5 bar as 1. Now if x5 bar is only 1, then you will choose x5 bar in the rainbow. Then the distance between q4 and x5 bar to q5 is exactly 2. Similarly, other extreme example is you can choose x6 and x7 bar. In that case also, you are choosing x6 and x7 bar, and the distance between x6 and x7 bar is exactly 2. So in a way, there exists a rainbow if and only if the LSAT is satisfiable. You can assign distances to other cases as well, where the clause is like this, or maybe like this. You can choose the distances like this, and you will have a assignment. Okay. So, other than this one, we have also showed in LSAT that decision version of rainbow minimax gap is NP-hard, and also rainbow piercing and rainbow covering is NP-hard. In the same LSAT formula. Okay. Now I'm going to another class of similar class of problems that I call exact cover problems. So here you are given a set of point color classes, that is a pair of points, and a set of point color classes, and your objective is to choose the minimum number of interval so that exactly one point from each color class is covered. Now the question is whether such a set of intervals exists or not. This is a certain different kind of problem. You can understand that. The previously what we are doing, we are given a set of color classes and a set of intervals. We are looking for a Pearson set. But here we are looking for given this color classes, we are looking for a set of intervals which covers exactly 1 point from each color. And we have showed that this problem is NP-hard for different classes when the intervals are even length. This is NP-hard. And this here version is NP-hard, version is NP-hard. Also, when the intervals of arbitrary, that problem is NP-hard. We have shown that in one of our papers. But after publishing it, we came to know about another problem known as binary Payne-Shaw problem, which is basically the same problem where they have proved that this problem is NP-hard. But still, we have other problems that we have proved NP-hard, like in 2 dimension. Think of this problem as a covering by say boxes or circles, and you have assumed that the points are unit distance apart. Each pair of points is unit distance apart. Even then, the problem is hard. There are many such cases. So you can take any coloring, any piercing problem, and find it into this multiple choice problem, and then you can have your approximation algorithm and approximations. So another problem is that in this setting that I want to discuss is that suppose again we are given a set of pair points, that is color classes, and you are given a set of conflict-free intervals. What do we mean by conflict-free intervals? These intervals do not contain both the points from the same color class. One way is that this set of intervals are not given. You create your own set of conflict-free intervals. That is, intervals that do not contain the points from same color class. And you want to try to cover all the color classes. Both this problem might be hard. Okay? So we have a 2 approximation algorithm when the intervals are not given to us, and a 4 approximation when the intervals are given to us. No, you want to choose the minimum number of conflict-free intervals so that each color class is covered at least once. It can be covered more than once, but you have to cover each color class at least. Yes, you can use. It's not. Okay. So this is the given set of intervals, and I show a 4 approximation algorithm for this. So how to do this? Initially, we are not able to get an approximation algorithm. So we thought that what happens when the intervals are disjoint? Can we solve it? Can we say something about that? Okay. So let me explain the algorithm first. That is, first how we are creating the disjoint intervals. We start with the first point and look at the intervals that cover this first point. And look at the interval that goes furthest. Okay. And choose that interval. Okay? Now look at the first point that is not covered by this previous interval, and the intervals that covers them. Now choose the interval which goes furthest and chop this interval off from the, you delete just the intersection with this interval. Okay? In this way, you will get a set of disjoint intervals. Okay? Can we say something about this? Can we solve this? Can we have an approximation? Okay. And if you look at this, this is nothing but a vertex cover problem. Why? Each interval you can consider as a vertex, each color class represents an edge. Right? Think about it for a moment. Each interval is a vertex and each color class is an edge. And this is exactly what is covered. So what we can say that right? But okay, we have a two approximation when the interval is disjoint. So what? What have we done? Okay. Look at the optimal solution when the intervals are not disjoint. Okay? Now, suppose this is one such interval in the optimal solution. How many intervals from this disjoint set of intervals will cover this interval? Suppose in the way we have discarded many intervals. Suppose this is one of such intervals. Why we have discarded it? Because first of all it has to be covered by somewhere here, and then we have discarded it because it's not the farthest. After this interval, this is not the farthest running interval, right? So we have selected the interval that runs furthest. So you can see that together these two intervals completely contains this interval. Hence, any solution here is a two approximation to this. Any solution to the disjoint case is a two approximation to the original case. Hence, we have our four approximation. And as a concluding remark, that we have proved many such gradients to be entity hard and presented many approximation results. We also considered certain problems of this for the approximation algorithm that in R2. In R2, what we are trying to do is, given a set of pair of points in R2, we are trying to find exactly one point from each color class. So the minimum Euclidean spanning tree is minimized over all choices. That we have an approximation algorithm for that as well. And I think this is a new set of problems, and there is a lot of open problems because, as I said earlier, that you start with any problem, any geometric setting, even non-geometric setting. Start with any covering problem, and you introduce a choice in that setting, and you will get a new multiple choice problem. And I think those problems are interesting, and you can also think of a variant where each color class contains more than, say, 2 points, 3 points, 4 points, 5 points, maybe k points. You can parameterize something on k or not. And again, what are some other geometric objects that you can consider? Maybe where there is a question mark, because you can consider objects which are not even geometric. Just think it's this problem in different settings, and you will get many problems. And there are many open problems in the set, and you can define it.